Okay, so for our first lesson of Chapter 2, we're diving a little bit farther into particular triangle relationships. So the main focus of this unit, or this chapter, is special right triangles, or right triangles in general, and looking at how that actually appears on the unit circle. So we've done only like the quadrantal angles before, so now in this chapter, the big idea is looking at other potential intersections with like a 30-degree reference triangle, a 45-degree reference triangle, or a 60-degree reference triangle. So today you should remember the special right triangles, but today we're just going to kind of go through that a little bit and uncover the relationship that is formed between them. Now again, the main part that's different about this class versus the other classes that you've taken is that these derivations that we do, so actually coming up with the fixed ratio of our special right triangles, so 45, 45, 90 or 30, 60, 90, are things that you should know. You should know how to do that and how to replicate that and explain where those things come from. So we're going to go through one of our derivations. The other derivation is for you to try on your own. Okay, so the first thing that we're going to do is, I know you probably don't have a ruler, but kind of bear with me a little bit. At least I'm going to show you how these special right triangles come into play. So I'm going to draw a triangle in the corner, and I'm going to mark it off at about 2 inches on either side. And this again is my 45, 45, 90 triangle. I'm creating some, isosceles triangle here. So here's my right angle, and then each of these are my 45-degree angles. Now I measure these as 2 inches and 2 inches. So now I'm going to measure my hypotenuse. So that's about, what is that, 2.1. So 2 14/16. So that's 2 7/8. So I'm going to figure out what that is as a decimal. So 2.875. Now, again, obviously our hypotenuse is the larger side. So what we're going to do is we're going to come up with the ratio between the hypotenuse, which I found was 2.875. And each of my legs were 2 inches. And that ratio ends up being 4.4375. Now, if you did this, you might have, obviously I've had some user error because I'm not perfect and I maybe didn't measure it super amazingly, or, maybe my ruler that I have is not perfect. But if we did this enough times and we did this with enough people, with enough trials, we'd uncover that everyone's ratio would end up being a similar ratio in this fixed number here. So all those, no matter how many, like what kind of sides you drew, if you did like 3 inches or 10 inches or 1,500 inches, whatever it is, all these triangles are similar triangles, and they always have this fixed ratio of my sides. So we're going to figure out what that fixed ratio actually is in our derivation. And you might already know, but this will kind of help us guide to that point. So if I started with my triangle here, this is my 45, 45, 90 triangle. I'm going to start with the things that I know about 90 or right triangles, things that we've been using pretty much every day in this class is the Pythagorean theorem. It's super useful. So I'm going to label my sides as A, B, and C. So I'm going to start there. I know that this is true for any sort of right triangle, but specifically this one. But I have a special case in my 45, 45, 90 triangles. I know something about A and B, that it's an isosceles triangle, so A is really equal to B. So this gives us our special kind of trick so that we can actually do something with the Pythagorean theorem. So on the back, again, for that derivation, there is a special trick that goes along with it. There's something that you could do here, like that makes this triangle special, and you have to use that special case to build into your Pythagorean theorem to see what kind of ratios come into play. So for this special case, I know that A equals B, so I can make that substitution here. So I can say that B is equal to A or A is equal to B, either way. So if I make that substitution, I really end up with A squared plus A squared equals C squared. So that combines to 2A squared equals C squared. And again, I'm coming over a ratio of the hypotenuse over leg. So what I want to end with, this is where I'm going, I want this. That's what I want my ratio to be, because that's what I'm looking up here. I did the hypotenuse over my leg, and my hypotenuse is C, and my leg is A. So that's where I want to end up with my derivation. So to solve then for that, I'm going to divide both sides by A squared. So those cancel. I'm left with 2 equals C squared over A squared. And then to get this, so that I actually have C over A, both those quantities are squared, so I can take the square root. So I end up with the square root of 2 equals C over A. And technically, again, this is positive or negative, plus or minus, but this is talking about side lengths and triangles, so I know my ratio is going to be positive. So the square root of 2 is approximately what we actually came up with, at 1.4375. Actually, the square root of 2 is approximately 1.41242. So we are actually pretty close. Obviously, mine was a little bit bigger, so I must have, measured slightly wrong or had some user error, or my compass or my protractor ruler wasn't great. But this is where we're ending up with. So every 45, 49, 90 triangle will have this relationship. So in a general case, the hypotenuse is always equal to root 2 times the length of the leg. So if my length of my leg is x, I know that these two things are equal, x and x. So my hypotenuse would be x times root 2. So let's do an example where we're finding the exact length of the legs. This time we're given the hypotenuse. So you can I know in geometry we had a proportion. You might have been familiar with that. We're going to use it as just a generalized example or a generalized equation where we're generalizing what we just set up here. The hypotenuse is always equal to root 2 times the leg. And that allows us to make those substitutions. So my legs here are x and x. So my hypotenuse is 7. And my leg is x. So to solve for my leg, I have to divide both sides by root 2. And we know we can't leave it like that, so we got to rationalize. And we'll get 7 root 2 over 2 for each of my legs. So that would be the exact length here. Okay. So that's all of my special right triangles. That's all of my 45, 45, 90 special right triangles. We have one more special right triangle we're going to look at, and that's an equilateral triangle. And to do this, again, we're going to kind of construct this equilateral triangle, but it's not going to be perfect. So I am going to make, again, a triangle of 2, 2, and 2. I know in my equilateral triangles, actually this might actually work out nicely. I should have approximately a 60-degree angle here in the corner. It's my first shot of it, and it looks pretty good. Nice. So there's my equilateral triangle. All my sides here are 2, 2, and 2. And all of my angles here are 60, 60, and 60. Now what happens, this one too, but what happens with an equilateral triangle or getting a 30, 60, 90 triangle is we start with this equilateral and we drop down the altitude. And what that does is it creates a 90-degree angle. It takes this 60-degree angle at the top here and splits it into 30, 30, and 30. And it also splits this length here into 1 and 1. So if this were, 4, 4, and 4, this would be 2 and 2. So that's one of the special relationships that we have, just like the 45, 45, 90 triangle, where we're trying to come up with something special so that we can use Pythagorean theorem here. This is one of the special things that we have, is that the hypotenuse of my triangle is always twice the length of the smallest leg. Okay, now you're trying to find, and I'm going to tell you where we're going to try to end here. Oops. We're going to try to end with, again, some sort of ratio. But for this one, we already know one of the ratios or one of the special relationships that we have. So if, again, we label our triangle as A, B, and C, I know that these relationships are true. Like my hypotenuse is always twice my leg, so you can kind of come up with that and use the Pythagorean theorem. But I'm going to tell you that we're trying to end with the ratio of, well, we're trying to end with C over B, and we also kind of want to end with or A over C, like, or A over B. One of the two. We're going to try to figure out what the ratio is between that. So that's kind of where you're headed. I'm just going to tell you what you should get, because then this is your job to like kind of finish this and try this derivation on your own. You should end up with something to do with root 3. So in our case, our 30, 60, 90 triangle, the smaller leg times root 3 is always equal to the bigger leg. So in our generalized case, again, if this is my smaller leg, across from my 30-degree angle, my hypotenuse is always twice that, so 2x. And then you should also get that your bigger leg is root 3 times your smaller leg. So that's our generalized case. So we're going to go through that and just, because this one's a little bit harder, we're going to go through and do 4 examples to look up, or try to figure out what the other side lengths are, or the angles of our 30, 60, 90 triangles. So let's start here. We are going to find the other side lengths of this 30, 60, 90. Right now I'm given my hypotenuse, so I need to find my smaller leg, my short leg, so I'm going to call that A, and I'm going to find my bigger leg, which is B. So I know that my small leg, so A is going to be since my hypotenuse is twice the length of the smaller leg, I know my hypotenuse is always twice my smaller leg. I know that my hypotenuse in this case is 5. So I can just divide that by 2 to find my smaller leg. So A is going to be 5 over 2, or 2.5. And then my bigger leg is always equal to root 3 times my smaller leg. So in this case, B, which is this part right here, is going to be root 3 times A. So I know that A is 5 over 2. And just multiply those things together. This is really like root 3 over 1, so you can just multiply the top, and we get 5 root 3 over 2. Okay, we're going to do the same thing, except we're going to start here with number 7, or start here with example 2, with 7 given as my long leg. So again, I know that I'll write it out here, smaller leg times root 3 equals my bigger leg, or longer leg. Right now I'm given my longer leg is 7. So I'm going to label my short leg here as A. So I have A times root 3. So to solve for A, just like on the front, we got to divide both sides by root 3, and then we'll have to rationalize. So we should get 7 root 3 over 3 is my shorter leg here of A. And then once you have the shorter leg, like that's kind of the key factor here, is once you have your shorter leg, then you can find all the other ones. My hypotenuse is always twice my longer leg, shorter leg. So if my short leg is 7 root 3 over 3, then my hypotenuse, which I'm going to label here as C, is always twice that. So 2 times that 7 root 3 over 3, which is just 14 root 3 over 3. And 5 over 2. Sounds a little bit harder given the longer leg, but you can really work around anything to get to those places. So if I gave you that, originally that in this triangle this was 2.5, you could double it to get your hypotenuse, and then you could tack on the root 3 to get your longer leg. For this one, we're actually coming up with the angle relationships. So first thing that I notice is that this is some 30, 60, 90 triangle because I have a root 3 that's involved. My shortest side always goes along with along with a 30-degree angle that's across from it. So between two 2/5, 1/5, and √3/5. 1/5 is my shorter side. So that means that the measurement of angle G is going to be my smallest angle, which is going to be 30 degrees. But I can always tell that too because I know that my hypotenuse, which is this one, is always double my short leg. So if I can find my hypotenuse and I can find what's half of that, or vice versa, then I can label my 30-degree angle. So that means that this is my hypotenuse, which means that obviously angle F is going to be my 90-degree angle because it's also labeled, but also it's across from my hypotenuse. And that means that the measurement of angle E is my 60-degree angle. And this should hold true, like if this is X, this is 2X, and this is √3X. This one looks a little bit more complicated, but again, what I look for first, obviously we know that the measurement of angle C is going to be 90 degrees, but what I look for first is I look to see if there's a relationship between my hypotenuse and if any of my legs are half that. So 16√3/3, I can already see that across from my angle A is 8√3/3, so that means that A is my 30-degree angle, and that means that C is my 60-degree angle. So when we come back and we work on this, again, your job here is to work on your derivation and complete that and look at those 30, 60, 90 triangles and try to come up with like one of these ratios at the end to see if you can kind of factor in that √3. But again, what you're going to start with is a Pythagorean theorem. And this is something that like I'll be checking when you come back, and then we'll practice coming up with all the different side lengths and we'll get really good at it. You might not even have to do like all these steps anymore because we'll be doing this so much that it will be kind of ingrained in your brain.